Bismillah ar-Rahman ar-Rahim. This is subject of general science, and today we are going to study about lecture number 26, which is about ideal gas equation. The outlines of the lectures are introduction, then key concept of ideal gas equation, then ideal gas equation, then calculating volume of ideal gas. First of all, we will see that what is the key concept of ideal gas equation. An ideal gas, which is known as perfect gas, is one which obeys Boyle's law and Chor's law exactly. An ideal gas is defined as one in which all collisions between atoms or molecules are perfectly elastic and in which there are no intermolecular attractive forces. In such a gas, all the internal energy is in the form of kinetic energy, and any change in internal energy is accompanied by a change in temperature. An ideal gas obeys the ideal gas law, which is known as general gas equation. The term ideal gas refers to a hypothetical gas composed of molecules which follow a few rules. Like ideal gas molecules do not attract or repel each other. The only interaction between ideal gas molecules would be an elastic collisions upon impact with each other or an elastic collisions with the walls of the container. Ideal gas equation is PV is equal to small n RT. Now, if we explain that what does it mean P, V, small n, R, T. So P means pressure, V means volume, N is equal to moles of gas, and T is equal to temperature. So here it is necessary to explain that what does it mean P, V, N or NT, because in the next phase we shall use just these abbreviation for solving any numerical problems. So that's why here this is necessary to explain that what is the meaning of these alphabets. Those are being used in ideal gas equation. An ideal gas is one that follows the gas laws at all conditions of temperature and pressure. To do so, the gas would need to completely abide by the kinetic molecular theory. A real gas is a gas that does not behave according to the assumptions of the kinetic molecular theory. Capital R, this is the gas constant dependent on the unit of pressure, temperature and volume. Where this constant R is equal to 8.314 joule per Kelvin per mole. If pressure is in kilopascals means K and P small a. Volume is in liter and that is represented by L. Temperature is in Kelvin and for Kelvin we use the symbol K. An ideal gas, this is a theoretical gas composed of many randomly moving points, particles that are not subject to interparticle interactions. The ideal gas concept is useful because it obeys the ideal gas law, a simplified equation of state, and is amenable to analysis under statistical mechanics. The requirement of zero interactions can often be relaxed if, for example, the interaction is perfectly elastic or regarded as point-like collisions. Under various conditions of temperature and pressure, many real gases behave qualitatively like an ideal gas, where the gas molecules are atoms for monatomic gas that plays the role of the ideal particles. So many gases such as nitrogen, oxygen, hydrogen, noble gases, some heavier gases like carbon dioxide and mixtures such as air can be treated like ideal gases within reasonable tolerances over a considerable parameters range around standard temperatures and pressure. Generally, a gas behaves more like an ideal gas at higher temperature and lower temperatures, as the potential energy due to intermolecular forces becomes less significant compared with the particles' kinetic energy, and the size of molecules becomes less significant composed to empty space between them. So 1 mole of an ideal gas has a capacity of 22.710947, and that becomes about 13 liters at standard temperature and pressure. A temperature of 273.15 Kelvin and an absolute pressure of exactly 10 raised to power 5 Pascal as defined by IUPAC since 1982. R is equal to 0.0821 ant liter atmospheric or atomic per atoms per Kelvin per mole. If pressure is in atmosphere, this is also atmosphere, volume is in liters, L, temperature is in Kelvin, K. Okay, here are some key concepts like an ideal gas is modeled on the kinetic theory of gases, which has 4 basic postulates. Gases consist of small particles which are in continuous random motions. This is one of the postulates. The other one is that volume of the molecules present is negligible compared to the total volume occupied by the gas. Then intermolecular forces are negligible. And the fourth concept is pressure is due to the gas molecules colliding with the walls of the container. The ideal gas models tends to fail at lower temperature or higher temperatures. We can say that if your temperature is either low or if your pressure is higher, when intermolecular forces and molecular size becomes important. It also fails for most heavy gases, such as many refrigerants, and for gases with strong intermolecular forces, notably water vapor. At night pressures or at high pressures, the volume of real gas is often considerably larger than that of an ideal gas. At low temperatures, the pressure of the real gas is often considerably less than that of an ideal gas. At some point of low temperature and high pressure, real gases undergo phase transitions such as to the liquid or a solid. The model of an ideal gas, however, does not describe or allow phase transitions. These must be modeled by more complex equations of state. The deviations from the ideal gas behaviors can be described by dimensionless quantity, the compressibility factors. So the ideal gas model has been explored in both the Newtonian dynamics as in kinetic and theory and in quantum mechanics as the gas in a box. The ideal gas model has also been used to model the behavior of electrons in metal, in the Drude model and the free electron model, and it is one of the most important models in statistical mechanics. If the pressure of an ideal gas is reduced in the throttling process, the temperature of the gas does not change. If the pressure of the real gas is reduced in a throttling process, its temperature either falls or rises, depending on whether its Joule-Thomson coefficient is positive or negative. The other key concepts are real gases deviate from ideal gas behavior because at low temperatures the gas molecules have less kinetic energy, move around less, so they do attract each other, and at high pressure the gas molecules are forced closer together so that the volume of the gas molecules becomes significant compared to the volume the gas occupies. The other key concepts are under ordinary conditions, deviations from ideal gas behavior are so slight that they can be neglected. Although there are three basic classes of ideal gas, the classical or Maxwell, Boltzmann ideal gas. The second one is the ideal quantum Bose gas composed of bosons, and the third one the ideal quantum Fermi gas composed of fermions. The classical ideal gas can be separated into two types: the classical thermodynamics ideal gas and ideal quantum Boltzmann gas. Both are essentially the same except that the classical thermodynamic ideal gas is based on classical statistical mechanics, and certain thermodynamic parameters such as the entropy are only specified to within an undetermined additive constant. The ideal quantum Boltzmann gas overcomes these limitations by taking the limit of the quantum Bose gas and quantum Fermi gas and the limit of high temperature to specify these additive constants. The behavior of a quantum Boltzmann gas is the same as that of the classical ideal gas, except for the specification of these constants. So the results of quantum Boltzmann gas are used in the number of cases, including the Sacher-Tetrode equations for the entropy of an ideal gas and Saho-ionization equation for the weakly ionized plasma. A gas which deviates from ideal gas behavior is called non-ideal gas. Now here this is an ideal gas equation. Before going through this Bayes law, an ideal gas is defined as one in which all collisions between atoms or molecules are perfectly elastic and in which there are no intermolecular attractive forces. One can visualize it as a collection of perfectly hard spheres which collide but which otherwise do not interact with each other. In such a gas, all the internal energy is in the form of kinetic energy, and any change in internal energy is accompanied by a change in temperature. An ideal gas can be characterized by three state variables: absolute pressure, volume, and absolute temperature. So the relationship between these variables may be deduced from kinetic theory, and that is called ideal gas law, and that equation is PV is equal to nRT. So we can extract it from Bayes law and Charles law and Avogadro's law. Like Bayes law that states that volume is directly proportional to 1 upon P. In other words, we can say that volume and pressure are inversely proportional. Means when we increase the volume, then pressure will be decreased. And if we decrease the pressure, then decrease the volume, then pressure will be decreased. And at constant N and T, number of molecules and temperature, then Charles law, as it is stated that volume is directly proportional to temperature, and this is at constant N and P. And at Avogadro's law, volume is directly proportional to N, and that is at constant P and T. So volume is directly proportional to N divided by T into P. Because volume is here is proportional to 1 upon P, then volume is directly proportional to T, and then volume is directly proportional to N. So when volume is directly proportional to these three things, 1 upon P, T, N, then we can write down V is directly proportional to N divided by T and P. So when we converted from directly proportional to equality, sign of equality, then it means that V is equal to constant into NT divided by P. Clear? So here T is at above side and mistakenly written here. This is basically V is directly proportional to NT divided by P. Because here we can see that T and N, this is directly proportional. So T and N will remain on numerator, and in denominator there is only P. And after converting it into sign of equality, so we can say that V is equal to constant into NT divided by P. Now what is constant? So here we use capital R, the ideal gas constant, and we can write down R into NT divided by P. And here we shall shift this P, which is in dividing. Here it is dividing, and when we shall convert it from this side to left side, then it will be multiplied with P. So we can write down PV is equal to nRT, and that will become your ideal gas equation. Here small n is the number of moles. Capital R, this is universal gas constant, and its value is 8.3145 joule per mole per Kelvin. Clear? And if we denote it N with capital N, it means that number of molecules, and K, that will be equal to Boltzmann constant, and its value is 1.38066 into 10 to the power minus 23 joule per Kelvin. And we can write down K is equal to R divided by Na, and N at base A is equal to Avogadro's number, and that is equal to 6.0221 into 10 to the power 23 per mole. Universal constant, universal gas constant. The conditions 0 degree centigrade and 1 atmosphere are called standards temperature and pressure. This is what we call STP. Experiments show that at STP, means standard temperature and pressure, 1 mole of an ideal gas occupies 22.414 liter. And we know that ideal gas equation PV is equal to nRT. And from here we can write down that with R, N and T, these are multiplying with R, and when we shall shift it from right side to left hand side, so it will become R is equal to, and we can write down R on left side, and then the quantity where it is written on left side, it is wholly can be shifted on right hand side, so it will become PV divided by NT. Then at STP, means standard temperature and pressure, value of capital R, that is equal to 1 atmosphere into 22.414 liter divided by 1 mole into 273.15 Kelvin, where capital R is equal to 0.082057 liter atmosphere, and this is per mole per. Now ideal gas law calculations. Remember that ideal gas law can be viewed as arising from the kinetic pressure of gas molecules colliding with the walls of the container in accordance with the Newton's law. But there is also a statistical elements in the determination of the average kinetic energy of those molecules. The temperature is taken to be proportional to this average kinetic energy. So this invokes the idea of kinetic temperature. 1 mole of an ideal gas at STP occupies 22.4 liters. Calculating volume of ideal gas, and that is equal to V is equal to N RT divided by P. Although it is equation of ideal gas equation, PV is equal to nRT, because here if we convert it if in multiplication, then it will become 1 upon P, and we can shift that P toward left hand side, and that will become PV is equal to nRT. So this is again the same as we have ideal gas equation. So what volume is needed to store 0.050 moles of helium gas at 202.6 kilopascals and 400 Kelvin? As we know that PV is equal to nRT, and the amount, or we can write down the values. P is equal to 202.6 kilopascals, and N is equal to 0.050 mole. T temperature is equal to 400 Kelvin, and volume, we have to find out the volume in liter, and capital R is equal to 8.314 joule per Kelvin per mole. Now 202.6, that will be equal to 0.050 into 808.314 into 4. This is as per PV is equal to nRT. 202.6 that is equal to P. Then at V as it is equal to N, small n, that is equal to 0.050 mole, and capital R, we know that 8.314 joule per Kelvin per mole, and then T for temperature, and that is equal to 400 Kelvin. So after multiplication, its answer will be 166.28, and V is equal to 166.28 divided by 202.6, and the value of volume that will come 0.821 liter. If we want to calculate the pressure of ideal gas, then again we shall use this equation. P is equal to nRT divided by V. Before this time we have divided P, but now we have to calculate pressure. So pressure is equal to nRT divided by V. Now the question is that what pressure will be exerted by 20.16 gram hydrogen gas in a 7.5 liter cylinder at 20 degrees centigrade. Now see that as we have taken this equation, PV is equal to nRT. Now what was the P? Because we have to calculate pressure, and then volume is given 7.5 liter, and small n, that is equal to mass divided by double M. Mass is equal to 20.16 gram, and mm h square is equal to 2 into 1.008, and 2.016 gram per mole, and n is equal to 20.16 divided by 2.016 is equal to 10 mole, and value of T temperature is equal to 20 degree, and we shall convert it from centigrade to Kelvin. So we shall add 20 plus 273, it will become 293 Kelvin, and then R value of R is 8.314 joule per Kelvin per mole, and just we shall use equation PV is equal to nRT, and this is P, and value of V is 7.5, N 10 or 8.314 into T 293, and P into 7.5 is equal to 24360.02. This is this came in after multiplication, and P is equal to 24360.02 divided by 7.5, because here 7.5 is multiplying, and when we shall shift it from left hand side to right hand side, so then we shall write down in division. Then P is equal to 3248 kilopascals. So this is what that we got after multiplication 7.5 on this value. So now if we calculate the value of mole of gas, again n is equal to PV divided by RT. So we can also, so this is also a numerical that we can solve. We can take values, and just we have to put all these values, and gas this temperature by finding out the values, and all these values we can write down, and just by putting in equation we can get value of temperature. So other problems that may be like that, hydrogen gas thermometer is found to have a volume of 100 centimeter cube with when placed in an ice water both at 0 degree centigrade, when the same thermometer is immersed in boiling liquid chlorine. So the volume of hydrogen at the same pressure is found to be 87.2 centimeter cube. So what is pressure? What is the temperature of boiling point of chlorine? We can also do it like this equation P is equal to nRT, just by taking the values and then putting in that equation its value, and we can find out after multiplication, and after multiplication we can get. So this was all about this lecture. Allah Hafiz.